Good morning, this is Dr. Heidelberg, and today's presentation will cover motion control basics. We are in Module 11, and we will open up Lecture 10A. The lecture will cover motion control. The topics that we will discuss in this presentation include controller architecture trends, high-speed network communication, industrial robot controller example. Then we'll talk about the proportional, integral, and derivative control filters. And we'll see a PID training tool that I developed as part of my company, Optinet. And we'll also take a look at what MATLAB is offering in servo system analysis tools with Simulink. The controller architecture trend, to get an overview, we will recall the analogy between a human body and a robot system. We have the brain of the human body is analogous to the motion controller. And then it is connected to the spinal cord with nerves into the muscles, the skeleton into the various body elements, knees, wrists, elbows, and the equivalent is the field bus, the various sensors that the robot is using, motors, frames, joints, fingers, visions, and arms. The basic scheme that shows the position of the motion controller within the environment of the automation system is given to us here. We saw it earlier in the course. It is being commanded with a PLC, which controls the entire process, and the robot motion controller, which we'll focus today, is controlling the motion of each one of its degrees of freedom through a servo amplifier into a motor, into the link. The basic configuration of a servo system traditionally, which was using plus or minus 10 volt commands from the motion controller into the servo amplifier, plus or minus 10 volts. Then the servo amplifier provides a high power, takes the 10 volts and amplifies that to high power into the motor, and the encoder at the back of the motor, which senses the position of the rotor, is being fed back to the motion controller. So that's the closed loop servo system, very typical. The earlier phases of servo controllers used to include a motion controller that had a position loop in it, and we see that other than position loop, we have also velocity loop and current loop, and the motor feedback is feeding back to each one of these loops some feedback signal. To the position loop, it feeds the encoder signal. To the velocity loop, it feeds in the velocity signal, the derivative of position. And to the current loop, it feeds in the actual current which flows through the motor coils. Each one of these loop is feeding into the inner loop. So the outer loop is a position loop, velocity is the middle loop, and the current loop is the inner loop. The controller starts with a trajectory generator, which sets the trajectory for each one of its axes, and together all the axes have to operate in synchronization in order to produce the desired motion at the end of arm, where the tool is located with the gripper or with any other device. The trajectory generator is considering a certain series of points, typically every millisecond. There is a target velocity, as we see in this motion profile, and the sequence of all these target velocities, when they are connected by straight lines, generates intermediate target positions for the controller to compare that with the feedback that it receives from the encoder, and then take the difference, and this is defined as the position error, and that position error is being acted on by various filters, as we'll see in a minute. The more complex way of segmentating the positions between each one of these targets is to use the so-called spline function. So if we know, for example, for each one of these segments, each one of them may be of a certain type. We see here different length, could be millisecond, 2 milliseconds. For each one of these segments, if we know the position at the initial phase, and the velocity at the initial phase, and the position at the final phase, and the velocity at the final phase, then we can generate a curve, a third order curve, which has the description of A times t cubed plus B times t squared plus C times t plus a constant t. And then, if we know the velocity and position here, and velocity position here, we can solve these four equations and four unknowns. We can put the initial position and the time at that initial position for this particular equation. Then we can put the velocity at the initial position and the time at the initial position, get the second equation, and at the end position, velocity and position, and we can solve the three equations and then find a curve which will be providing the target position in a more precise fashion than just a straight line. The next generation of motion controllers is a so-called servo drive system, where the controller is not providing a plus or minus analog signals of 10 volt, but rather a digital signal into the digital servo. So previously it was an analog servo that received plus or minus 10 volts, and here it is a digital servo that receives in a field bus a target velocity from the position loop, which is being generated from the trajectory and the feedback that the controller receives from the encoder, and that target velocity is getting into the servo drive. The servo drive does the intermediate loop with the velocity loop, and then commands the current loop, which in turn provides a signal to the motor. And here the commands are going through the field bus in the loop such that each one of these servo drives is in receiving mode. When it gets its address, it will recognize its command and will function accordingly. We see here a more advanced system, which is a so-called distributed approach of servo controllers, when the controller is responsible for just generating the trajectory for each one of the axes, and then the servo drive is a smart servo that has the position loop, velocity loop, and torque loop, and also its own trajectory generation, perhaps with flying function based on the trajectory generator, which is at a slower rate coming in from the controller. And again, this goes through the field bus into each one of the axes. We see through the years that the field bus has evolved into various open architecture or proprietary architectures of some companies. And here, for example, we see a controller area network architecture with a trajectory generator, as we saw earlier, on a field bus, and sending the datagrams to the entire network, and each one of these axes will act on it. And the typical configuration that we see over here, which is distributed field bus servo system, starting in the early 2000s, has an advantage that it could use a soft motion controller. It could be just a PC or a laptop to derive the trajectory, and then the controller can be connected through the CAN open network into the system. As we see over here, we have various devices, which are the controllers. We have the field bus here, and then each one of these nodes is receiving that command. It has the flexibility of adding more nodes without too much complexity. It has a capability of decouple the position loop from the host controller. Therefore, the host controller can operate at slower speed, and each one of the servo amplifiers does its own process, and the end result is much higher speeds. Also, the wiring is simplified and very well-established diagnostics to troubleshoot the errors in case they occur in the networks are provided in the CAN open field bus. We see one of the latest technologies starting in 2010. It's called the EtherCAT servo drive, which is high-speed Ethernet, where the control automation technology is being embedded within the Ethernet. And this is a typical servo amplifier, which includes also the servo controller. And what we see here are the various links to different types of feedback devices. Motor feedback could be analog or digital. We see over here different terminals for I/O. We have here the communication to the EtherCAT bus. And then we have over here some DC data link and power supplies. And then the power is coming in from the power unit into the motor. So that's a typical configuration of EtherCAT servo drive. We see that the servo drives in EtherCAT have a very high cycle update rate on the order of 16 kilohertz. And here is the entire configuration where we see that various measuring device and access controllers, servo amplifiers, and motion controllers are all connected through the Ethernet and high-speed EtherCAT. KUKA is a major robotic company in Germany, is using EtherCAT for controlling the robot, and it's having various advantages as they're specified over here, requiring no special hardware in the connection to the master. It simplifies again the cables, which means lower cost. There's a high data throughput rate. There's safety protocols which are provided with it, and the safety protocols are also related to the peripheral equipments, and it is widely used in industry, and several other slave devices are available through the EtherCAT, and there is a continuity to continuously develop the EtherCAT. We see other robotic companies such as Hitachi are including the Internet of Things in their robotic integrated system, where the robots are controllers are not only involved in axis motion controller, but also in other levels, including manipulator controller, cell controller, plant controller, supply chain controller, and including the enterprise resource planning demand controller. All of them are part of Industry 4 Internet of Things, which is an integration of robots into the social infrastructure to improve people's life. That's the theme of Hitachi robotic control system. As far as communications, we will not spend too much on it. This is pretty much our counterparts in the IT departments that are responsible for having the communication links between the controller and the various devices, robots, and peripheral equipment. But we'll just mention that the open system interconnection model includes 7 layers, which defines how protocols for communication are being established. There's the upper level application where the program is being generated. Then there is a data presentation to the various nodes. There is a control of the priorities of the data between the element. Then there's the way the data is being transported, whether it's a segment or a datagram, and it's going through the hardware network as packets, frame, all the way to the last physical element where it enters the device in single bits. We see here example of a packet. Again, we will not get too much into the details, but we see that each bit has a designated description. We see that 1 byte is 8 bits, a word is 2 bytes, 16 bits, and so on and so forth. And the segments of the datagrams are defined for each protocol accordingly, including how many bits will be the definition of the source port and the destination, the length of the data, and checksum to assure reliability of transmission. Here's another example of TCP segment structure, and another example of a CAN open structure. Now notice that the CAN open, for example, has only 3 layers of the OSI. It includes the application layer at the top, the data link, and the physical layers. So whoever is interested in actually developing a device to be connected with a CAN open would need to follow these protocol in order to assure compatibility. We see also various definitions for the IT folks, including the synchronous time window, and that is the time defined for what the transmission of the process data exchange a message and the receiving has to take place, and there's a cycle time between each one of these transmission cycles. We see various definitions over here of each one of the bits that comes in on, for example, a diagnostic element. For example, if the second bit is 0, then operator safety is not active, and if it is 1, operator safety is active. So these protocols have extensive elements of definitions for each one of these bits. Here's an example of programming with various diagnostic messages that the software engineers have to be aware when they do troubleshooting of any problems through the process. Here are some examples of robot controllers and their applications. Industrial robots are being manufactured by Fanuc, Yaskawa, KUKA, ABB, Universal Robots, and various other. There may be 100 different types of robotic manufacturers. These are some of the main ones, and the applications which are being used by the robots are arc welding, material handling, palletizing, pick and place, cutting robots, plasma welding, and many other applications. We are not going to go through all of these demos, but I suggest that when you look into the actual presentation, you click on that and take a look at some video examples. The controllers are many times integrated into the servo amplifiers of the robot. Here's an example of a 6-axis, and over here we have a 16-axis. So you see that the number of axes, of course, affect the size of the motion controller and its integrated servo drives, and then the environment protection is also a factor of the size. The environmental protection, so-called ingress protection or IP levels, are defined by 2 characters. The first character, the first number, defines the protection against solid objects, and the second one against liquids. So for example, if we have a system which is specified for IP 54, it means that it will be protected against dust and also against water sprayed in all directions. And of course, there could be various levels of these protections depending on the application. Here we see an example of the trend in robotic motion controller. We see that the controller box is pretty hefty and includes many features such as programmable motion controller. It has phase safety features. It has the robot motion controllers and many other communication links to kinematic analysis, sensor systems, and also to future safety technology that may be integrated in the future into existing controllers. So these are the trends, and we see that Internet of Things is the theme of many of today's controller manufacturers. The way an operator would program a system or teach a robot its motion typically is done through a teaching pendant, and this is a typical configuration of a robotic teaching pendant with a HMI here, with EMO here, and the HMI, and you can teach the robot we can jog it, teach it point to point, as we will be practicing in the lab with the Scobot. Here's an example of a robot controller. We take a quick look at this video, and this will give us an example of how things are being done. This is an example of KUKA, and what we see here is the flexible automation of a small robot. You see that the robot is brought into close proximity of a machine tool. The operator has the connectivity, it's plug and play, and he has a tray of parts. He secures the operation. This is the HMI. Just click and go, and he is now preparing the process. The robot is following a certain program to take a blank, place it into the measuring device, then place it into the machining center. Machining center is now operating on the part. The robot is waiting for the part to be finished. The robot picks it up. We see a nicely machined part, and he puts it back in a tray, and then he takes another part. We will not continue that, but I suggest that you take a look at that and see how that finishes off, together with all the other programs over here that you could see how the robot controllers are operating in various applications. Here's an example of a standalone controller, robot controller, and also various motion controllers, standalone motion controllers that can operate Cartesian robots of various types of number of axes. And here's the types of pendant that this particular company, Adept, is using. We also have extensive software which is being advertised as user-friendly for single or multiple robots, including programming conveyors, feeders, setting up I/O configuration, vision interface, 3D visualization, and diagnostic and multiple windows. So various companies will have various features in their softwares, and including the options to include the vision system to the robot controller. We will not take a look at the videos. I suggest you do that. We'll get right into the servo loops. And once again, we see here the three loops: the inner loop of the current loop, the middle loop of the velocity loop, and the outer loop of the position loop, starting with the trajectory generator, which is done at approximately 5 kilohertz, and then it generates the target position, The encoder sends in the actual position. The result is an error which goes into the motion controller. The motion controller passes with the PID the velocity command, and then this is done approximately at 20 hertz. This is the bandwidth of this loop, how fast this loop can respond. And then we have over here the velocity loop that gets the velocity signal from the encoder or the derivative of the position. And then the loop over here is a 10 times higher rate at about 200 hertz. These are typical values, of course, could be less or higher. And then the current loop is at a rate of about 2 kilohertz bandwidth for controlling the current which goes into the motor. The output over here is being controlled typically at a rate of, in robots, of 20 hertz position bandwidth. This is how fast the robot can follow a prescribed input sinusoidal function. Here's an example of a company called ACS that has its own motion controllers, high performance motion controllers using Ethercat network, and they can drive up to 64 fully synchronized axes at up to 5 kilohertz rate of function generation. We have here an example of an old servo control scheme with analog plus or minus 10 volts that we saw earlier. But here we see that the feedback position, theta, motor shaft, is feeding back into the summation junction, which gets the set point. And then the output is the error function that is being multiplied times a proportional gain called Kp, and an integral gain called Ki, and derivative gain called Kd, where the sum of all of them is the input to the servo drive. Outside the servo loop, we have feed-forward controllers which can either look at the expected velocity and the expected acceleration, and also add to the command into the servo amplifier or servo drive its contribution. And the advantage of the feed-forward controller is that we can increase the values or decrease the values, and it will not affect the stability. As we'll see later, the values of Ki, Kp, Kd may cause an unstable system, and we will see how to tune the system to eliminate that. Here's an example of feed-forward function. This is the velocity, this is acceleration, and the sum of it, which is added into the output of the PID controller. A tuning system, this is taken from Parker. By the way, most of these slides are referenced at the bottom with the source, so they are taken, and we of course thank the contributors for their information. We see over here the style of tuning. We could do this by trial and error, or we could do this by known systems like Ziegler-Nichols, and we'll take a look in a minute how it works. But an untuned system is one that has a very slow decay of overshoot, and a good system is one that when we give it a step function, the overshoot is limited and it decays very quickly. The process of tuning could be done by taking the system and then increasing the proportional gain until the system is starting to oscillate aggressively under no control, which is actually in resonance. And then we define that frequency or that gain as K0, and the frequency at which it happens at F0, and we set then Kp, Ki, Kd according to this formulation. So for example, Kp will be 0.6 K0, and Ki will be 2 times the frequency times Kp, and that is in Newton meter per radians per second, and similarly for the Kd. The analysis tool that I developed is shown over here, and this example, we could click on that and it will take us to a website where we could actually practice PID setup by changing the values in the yellow boxes and observing the results in the blocks over here. The example is obtained by clicking the example. This enters values in the yellow box, and then when we run it, we enter the results in the boxes also in the blue boxes. So let's see what we have in here. What we have here is a positioning system model where we have the reference set point position, we have the feedback from the encoder, we have the PID controller, and then we have the plant, which is the stage. Now the plant is a simple mass spring damper system, which is basically characterizing almost any mechanical system. These are the main characteristic of any system. Any actuator will have a mass, will have some stiffness, and will have some damping or friction. And we apply a force on it, and then we generate a displacement X. This chart shows the time domain step response. You see how it oscillates. And all of these charts show the frequency response. So we'll start with the plant frequency response. So in other words, if we just take the plant and we apply a force over here and we observe the displacement and we change the frequency of the force, we'll get a curve like this. We measure it in logarithmic scales by dB, and dB is 20 times the log of the output divided by the input, which is the basic gain. So what we'll see is that as we increase the frequency of the force, that the output is going to follow exactly without any overshoot. However, at a certain point, a certain frequency, the amplitude is going to be amplified, and this is the resonance frequency. And as we increase the frequency of the input to the plant, then the response output is going to decrease. Over here we look at the phase lag between what the output is doing versus what the input is telling it to do, and we see that at slow frequency the phase lag is very small, close to zero. As we increase the frequency at the bandwidth, it's 90 degrees, and then as we increase it to high enough, then we have 180 degrees off phase to the output. So we telling it to move upwards, but it is in the downward position. When we look at the PID frequency response just for this element over here of the controller, this is a rather unique description because it shows us how each one of these elements, the proportional gain, derivative gain, and integral gain, will affect this trough. I haven't seen this in any other literature, so I thought it's pretty innovative and unique for training, because what you see is that the PID is a trough. And what it does, it attenuates the area where the resonant frequency is happening. So when we combine the PID frequency response with the plant frequency response, we get the open loop frequency response. And the open loop frequency response is extremely important in telling us information of how stable the system is. We'll take a look at it later. And the open loop frequency response simply disconnects the feedback, and it tells us what the output is doing when we input a signal over here into the controller through the plant out to the motor. This is this response, both in gain and in phase. And the output closed loop frequency response is when we look at the response of the fully closed loop servo system, including the feedback. And we see here that as we go all the way to the bandwidth, the system follows with very little error. Then beyond the bandwidth, the system starts to losing information, and it has also a lag in its phase. Now, the input information includes the parameters of the plant, including the mass, stiffness, and damping, including the motor constant. And for the controller is the proportional gain, derivative gain, integral gain, and the set point where we want the step to occur. The output shows us the natural frequency, the damping coefficient, also the maximum current, the maximum power, the maximum jerk, the maximum acceleration. It also shows us over here the maximum velocity, and most important, the settling time, which is a criteria for the effectiveness of the tuning of the system. To work the system, we could see, for example, that when we decrease the damping over here from 900 to 500, we will expect this amplitude to increase. And what we do over here is we simply run it, and the system now is showing us that we actually change the frequency over here of the response. We change the performance, and also we increase the peak. And we can see also over here what is the settling time, which got a little higher. If we decrease the number from where it was before, let's say to 100, then we will expect this peak to be of different configuration over here. So now we have a lower damping coefficient, so the peak over here is getting higher. As we see, there's less damping, the oscillation are getting higher, and the time also is changing. We can also try to affect the performance by changing the derivative gain. We can make it, for example, 500, and see what effect this has on the system. We can run it, and typically the advantage of this system is that if we have any problems in changing the mechanical specification of the system, we can affect it by changing the PID parameters and try to improve this system. We see how all of these frequency response is changing, and we could actually go through the process and try to tune the system in order to get desirable performance. Here's another typical example of a servo block diagram. We see pretty much what we saw earlier. We have actual position from the encoder going into the summation point. We have a set point from the trajectory generator giving us the reference position. The arrow, which is the difference of the two, is getting into the proportional gain, derivative gain, and integral gain. This goes into the amplifier, into the motor. Disturbance is acting also and presenting different forces and torques on the system, and the summation of all of that is acting on the plant to give us the actual position. Here's an example of ACS company block diagram of their motion controller, basic one, and you see sometimes it's called PIV. We see that the desired position is being added to the negative of the position feedback to the proportional gain. This comes in with a velocity feed forward to the velocity loop, and this gets also a feedback of velocity from the derivative of the encoder position. And this also has an option of going into a notch filter. We saw earlier the trough. The notch filter is a very steep trough that actually filters out certain resonances, not a wide spectrum, but a very narrow spectrum. And then there's a low pass filter that allows low frequency to go through and filter out high frequencies, and there's also a proportional and integral filter which provides other means of making the system more stable. We have seen the demonstration of the system which I developed. This gives you different definitions and more descriptions for you to follow on a PDF, and this will actually showing us an example of an ACS stability of open loop diagram online. And the stability criteria is being determined by two factors. One is called the phase margin, which is the angle between the 180 degrees and the intersection of a vertical line going from the crossover frequency of the gain between the open loop line and the 0 dB. We come down all the way to the phase angle, and at this point we measure the phase, and the distance between the phase to 180 is called the phase margin, and we want that to be actually a positive number. We want that it will be less than 180 degrees, such that we will not feed in positive feedback instead of negative feedback. 180 degrees meaning that the feedback has a minus sign. It's exactly in the opposite direction. So minus and minus on a summation point is plus, and therefore the feedback is positive, and instead of controlling the system, we make it go uncontrolled. The other criteria is the gain margin. If we look at the intersection of the phase curve on a border plot, on a frequency response, and the 180, and we raise the vertical line all the way to the gain chart, then the distance between the dB, the gain at this point of intersection, and the 0 dB is called the gain margin, and we want that to be negative. We want to be at approximately minus 15 dB. Over here we want to have about 45 degrees phase margin for a good stable system. Why do we need a gain margin? Is simply not to amplify the feedback at a gain higher than 1 when the system is at minus 180 degrees phase shift. So when the system is exactly at the opposite position, we don't want to inject more energy into it to make it unstable. So this is the intuitive explanation to it. This shows us the closed loop bandwidth. Again, we see over here that up to the bandwidth, the system is pretty much following the command with very small error, and then after the bandwidth, which is this point over here, the intersection of the 0 dB and the and over here the gain chart. Beyond that, we see over here high frequencies that sometimes a notch filter can help that, and the response is being attenuated. The schematic presentation of phase margin and gain margin is shown to us here. We see over here the resonant peak of the plant. We see that the gain goes over here to a maximum at resonance, and this is a resonant peak. And over here we have at minus 3 dB over here, that is this is the point where the bandwidth is being defined. The open loop is shown over here as a straight line. This is the gain crossover, and we see that when we come down with a vertical line, it intersects the phase curve at this point, and this is the phase margin. The difference between this point and minus 180 is a positive number. We like it to be at about 40 degrees. And if we go to the intersection of the minus 180 and the phase chart with the bringing in a vertical line, it intersects the gain chart at this point, and this is a negative gain margin, which is good for a stable system at about minus 15 dB. We see over here the details of the presentation that we showed before for the tool which I developed, and here's a simple exercise that student may follow through and see how to go through tuning the system. Similarly, MATLAB is providing us very professional tools for simulating various closed-loop control system and doing extensive analysis by dropping down various function generators and scopes and various controllers and planes, and watching the behavior of the system, as well as tuning and bringing it to perfection. This concludes our presentation for motion controllers, and we will follow up with more exercises in a lab. Thank you.